Okay. So hi everybody. So it's I guess it's lecture 24. Wait, why is it showing me lecture 20? Okay, I'm a little confused by this. I'm just going to restart this. Okay, good. So it's lecture 24. And what we're going to do in this lecture is we're going to continue doing graph theory, more graph theory. And I just want to say the next few lectures, we're not really going to follow the book. So the book is, in my opinion, extremely disorganized. It presents the topics in an order which I don't think makes that much sense. So I'm going to follow a different order, and your main reference for this part of the course should just be the notes from the lectures. So in this lecture, let's see, we're going to do three things. So one is we're briefly going to review some terminology from last time. And we're going to prove some, we're going to revisit the bridges of Königsberg using this technology. And then I'm going to prove a simple lemma called the handshaking lemma. And then I'm going to show you some examples of graphs. Actually, I'm not sure what order I'm going to do this in. Yeah, maybe I'm going to have some running examples of graphs. And then finally, I'm going to introduce a new concept, which is a concept of two coloring a graph. And I'm going to prove interesting, not obvious theorem about two colorings of graphs. So let's start by recalling some terminology. So in the previous lecture, we defined, so here are the slides from the previous lecture. We defined what a graph is. And then we defined some English words that we gave a very precise meaning. So if E is an edge, so an edge is a pair of vertices, then we have various ways of saying that in English. We could say A is adjacent to B, or E is incident with A. E is incident with A means A is one of the endpoints of E, or A and B are the endpoints of E. These are all different ways of expressing the relationship between an edge and a vertex. So we have this basic terminology of a single edge and a single vertex, which is if you have an edge which looks like some vertex A connected to some vertex B by some edge E, then we use the terms adjacent, incident with, or endpoints of to describe this relationship. So E is equal to the pair AB. And then we developed some slightly more advanced concepts around this. So one is the number of edges incident with a vertex is called its degree. So let me draw a picture of this here. Let's say you have some vertex here, V, and then you have a bunch of edges coming out of it. So you have a bunch of other vertices that it's adjacent to. So these are sometimes called its neighbors. So you say A is a neighbor of B. It's the same thing. And then we define the degree of a vertex. So in this case, we're interested in this particular vertex V. We define the degree of V to be the number of edges incident with V. So in this case, that's 4. So degree of V is a number of edges incident with V. So in this case, the degree is 4 in this particular example. And I think that's all we did. Yeah, we talked about simple graphs. Simple graph means no repeated edges. So I want to build on this a little bit. I want to define a couple of more things that are going to be used to revisit this bridges of Königsberg thing in a more formal way. So one more definition I want is the definition of a path. So a path in a graph G is a sequence of edges E1, E2, E3, all the way up to En. So this is called a path of length n. So let's add of length n. That's the number of edges. It's a sequence of edges, not just any sequence, with the following property, such that there exist some vertices. So these edges are now in the edge set of the graph. And such that there exist vertices x0, x1, up to xn in the vertex set of the graph, such that EI, the ith edge, is the I minus first is has the I minus first vertex and the ith vertex as its endpoints. So that's the formal definition of a path of length n. Now, this may look a little clunky, but the picture associated with this is actually very simple. All it's saying is that there are some n plus 1 vertices. So notice that the number of edges is n. The number of vertices is n plus 1 because we start at 0. The picture associated with this is simply what you think. There are some vertices x0, x1, x2, all the way up to xn, and they are connected by edges in the graph. And the edges that they're connected by are these E1, E2, all the way up to En. So the picture associated with this is very simple, but this is the formal definition. Any questions about this definition?
Yeah.
Yeah, what question?
So the definition of the path is just when, so there are like a few edges like E1 to En, and what do you mean by there exist vertices x0 to xn such EI? So I just don't understand this, like
Well, so if I didn't put that, it would just be any sequence of edges, right? That's not a path. So the key property of a path is that the edges follow each other, right, in a path. And what that means is that if you have two edges that are every two pair of adjacent edges in the path have a common vertex. So that's one way of saying it is this. So let me write a few equivalent definitions. So equivalently, a path is a sequence of type x0, x1, that's one edge, followed by x1, x2, that's another edge. And in general, it's xi minus 1, xi, all the way up to xn minus 1, xn. It's a sequence of type this, where all of these things are edges. Or so we just write a sequence of edges. So this is saying the same thing. It's just saying that, the edge E1 consists of this, the edge E2 consists of this pair, and this is the edge En. Does that make more sense?
but does that have to be in a certain order?
Yeah, so the key point is that this x1 is equal to this x1. The order matters. It's a sequence. So sequence means the order matters.
So if it's like x1, x0, x1, then the next set cannot be x like 2 and x3?
Yeah, that's right. Because then these wouldn't be a common sequence. These wouldn't have a common vertex.
So a path is basically like the edges that connect themselves
Yeah, the
into
edges are
the envelope.
connected. Yeah, it's a very, you're right. So it's what you think it is, but writing it formally is a little bit annoying. Or here's another equivalently. So here's the safest way to think about a path. So you can also think of a path as, I mean, this is not the formal definition, but as a sequence of alternating edges and vertices, right? So you have x naught followed by e1, then x1, e2, x3, e3, all the way up to en, xn, such that ei is the edge, is the pair of vertices that are to its left and right. Right, so this is an edge, this is a vertex. So you can think of it as an alternating sequence of vertices and edges, but the formal definition is it's a sequence of edges. Okay, and so if you're confused, just think of it this way as well. So that's a path. Okay, so for example, let me show you an example of something that's not a path. So suppose you have a graph that looks like this, and you have two edges E1 and E2 like this. This is, so then the sequence E1, E2 is not a path, right? Because it doesn't have the structure that every two edges that are next to each other in the sequence share a common endpoint. Okay, I mean, let me write yet another definition. So equivalently, EI and EI plus 1 have a common endpoint. For every I going from 1 to n minus 1. So there are many ways to define it, but they all reflect this simple picture here. So any questions about any of these? Although actually, the last definition is not formally correct. So actually, why is this not correct? The last definition that I wrote. Well, okay. Let me put it this way. It is correct, but it requires some proof to say why having a common endpoint implies that you have the structure. So common endpoint just means that they share a vertex in common. That doesn't immediately imply what's written in this definition. What's written in this definition is a little bit stronger because it's saying that there are these n plus 1 vertices, and the middle n minus 1 of those are the common endpoints. So it is actually equivalent, but it's not obvious why it's equivalent. Okay, and so a path of length n has n edges and n plus 1 vertices. And there's some further slight terminology that's used. So a path is simple if no edges are repeated. So no edge appears twice. So for example, if you have a path that does E1, E2, and then E3 is the same edge again, this is not simple, right? Because because this last edge appears twice. And the interpretation of this is I'm walking along this path like this, E1, E2, and then I'm walking back. If I list out the vertices in this starred formulation. Okay, so let's oh yeah, and then one more thing, a path is a circuit if the first vertex is equal to the last vertex, if x naught equals xn. So the picture associated with this is that you start at a vertex, you take some steps, and then you end up back at the same vertex. Okay, so now using these concepts, let's revisit the proof of this bridges of Königsberg thing we did in the last lecture, right? So we said that there's no way to walk from A to A in this graph, crossing each bridge exactly once. And we wrote down what looks like a proof, but it didn't use, entirely well-defined concepts. So we talked about a walk here, right? But we didn't actually define what a walk is. So let's write this proof down a little more formally using these concepts that we used. So here's a theorem. Well, okay, we need one more concept for the theorem to state the theorem. So let me just use that. Oh, sorry. Well, no, this is okay. So let's just do this. So if a graph has an Eulerian circuit, so this is I guess another terminology. So circuit is Eulerian if it uses all the edges of a graph. If it uses every edge exactly once. The key property is exactly once. Okay, so the theorem that we're now going to just rewrite down a proof of, but a little more, a little more precisely, is if a graph has an Eulerian circuit, then the degree of every vertex in G is even. Okay, so let's prove this. Yeah. Sorry. So actually, okay, this is a little bit annoying. Sorry, I actually want to change the statement just a little bit. I want to add one more condition to make it a little bit cleaner. We have one more definition, which is the graph being connected. A graph is connected. So let's write it as a pair. Let's write down the vertex and the edge set explicitly. It's connected if for every pair of vertices, for every pair of distinct vertices x and y in the vertex set, so distinct means not the same, there is a path from x to y in G. So from x to y means the starting point is x naught and the ending point is xn. So this terminology is that this is a path from x naught to xn. Okay. So this is the definition of a connected graph. And let's look at some examples before we use it in a proof. So this is an example of a connected graph. For every pair of vertices, there's a path. In fact, there's actually an edge from one vertex to the other. This is an example of a connected graph. This is an example of a disconnected. This is not connected. That's because, for example, you can take x over here and y over here, and then there's no path from x to y. Okay, so now we're going to prove a theorem. It says if G is a connected graph and G has an Euler circuit, or an Eulerian circuit, I guess. Then the degree of every vertex has to be even. So let's write it like this. Okay. So this is a generalization of what we, in the last lecture, we proved this for this specific graph, right? This specific graph with 4 vertices and a bunch of edges. Now we're going to prove it in general. So let's prove this. So assume the graph is connected. So assume G is connected. And now it has an Eulerian circuit, so let's give it a name. So let's call it C, or actually, yeah, let's call it capital C, given by x naught, x1, x1, x2, xn minus 1, xn, be an Eulerian circuit of this graph. Okay. So now the first thing to observe is that this graph has to have at least 2 vertices. Otherwise, it doesn't have any edges. I mean, okay, I guess you could consider the graph with 1 vertex and no edges to have Eulerian. So okay, we could do it that way as well. So well, fine, let's just do that. So if V only has 1 vertex, then we are done. Otherwise, the graph has 2 vertices at least. So I can choose some vertex other than this starting point. So in this Eulerian circuit, there's a certain special vertex xn, which is equal to x naught. Right. So there's this picture that there's a special vertex x naught, and then there's some path like this. So the edges are not, they don't have arrows, but I can mark the direction of the path with these arrows. So now what I'm going to do is I'm going to choose a vertex other than the starting point, right? Otherwise, let V be any vertex other than the starting point. So let's choose a vertex V like this. Or maybe more interesting in this example, let's choose this vertex V over here. Otherwise, let V be any vertex other than X naught. Okay. So now observe that every time this circuit C visits this vertex V, it enters through an edge incident to V and exits through a different edge incident to V, right? So observe, it's the same observation. Observe that every time C traverses well, okay, so we haven't defined the word traverses, we haven't defined the word visits, but it's kind of clear from this context what it means. Every time this walk visits V, it traverses or it traverses two edges. Let's just give them a name. Let's call them AV. Well, okay, this is a little bit annoying. It traverses let's be a little even more formal. Let's do it this way. I guess you're seeing me write a proof in real time. So let's so assume this walk visits V some number of times, right? So assume C visits V exactly K, which has at least one times. So now I've put K on the table as well, right? So now the table has this path C, it has this vertex X naught, it has a vertex V, and I visit this thing K times. So in this particular example, how many times do I visit V in this C? Okay, can someone ask a question? Two. Okay, right, two. So in this cartoon, the sequence of edges that's marked as this is E1, this is E2, and so on. So I visit V once between E2 and E3, and then I visit it again between E4, E5, E6, and E7. So I visit, in this running example, I visit V, the vertex V twice. So assume C visits V exactly K, bigger than one times. And now for each visit, in each visit, C uses a pair of edges incident to V. So each time you enter and exit, you use two edges, right? You use one edge before and one edge after. And the key point is that because the walk is Eulerian, these pairs are disjoint. So because C is Eulerian, the K pairs of edges, or these K pairs of edges, are disjoint. as in no edge appears in two of these pairs, and every edge incident to V appears in a pair. Right, because if it didn't appear, then C wouldn't use that edge and it wouldn't be Eulerian. So I'm really using that C is Eulerian here for two things. I'm using that every edge incident to V appears, and these pairs are disjoint. No edge appears twice. So what that means is I've partitioned the edges incident to V into pairs. And that's all you need to say if the degree is even, right? I mean, in fact, the degree is equal to 2 times K. So I mean, let's just be more precise, into K pairs. So degree of V is equal to 2K as desired. Okay, so this is a formal proof of this fact that if you have a connected graph, if it has an Eulerian circuit, then the degree of V is even for every vertex V. But actually, I'm not done. There's one thing missing in this proof. Can somebody tell me what that is?
Do we need to talk about the initial point that we start and end at?
Yeah. So all we did is, so right now V is an arbitrary vertex that's not equal to X naught. So we just proved all of those have even degree, but we haven't done X naught, right? Now for the starting vertex, it's a little trickier. Any ideas on how to handle the starting vertex?
Would we be allowed to choose a different starting point for another Eulerian circuit, one that we know by the conditions here to be having even degree, and then basically use the same logic about this new thing?
Yeah, okay. So one idea is to modify C so that X naught is not the starting and ending point. That is one line of proceeding. You could do that. Any other ideas? That would work, but there's actually a somewhat simpler thing you can do. So the simple thing you can do is you can say, well, do the same thing with the starting vertex, but ignore E1 and En, right? For all visits to the starting vertex, except for the initial and last edge traversal. So I mean, yeah, let's be more formal. Let's use the word traverse. So the word traverse and visit is usually used in this. So these are some like keywords that are used in graph theory: traverses, visits. A path visits a vertex. A path traverses an edge. What we can do for the starting vertex is we can just say, well, okay, for the starting vertex, we just repeat the same argument, but for all visits other than E1 and EM. So for all visits to X naught other than via E1 and EM. So by E1 and EM, I mean the first edge in the circuit and the last edge in the circuit. And by which I mean the first occurrence only. If E1 is used later, that's okay. That's no problem. And what does this do? Well, this allows us to partition all the other traversals into pairs. So this yields a partition of all the other edges incident to x naught into pairs. And now you add, the point is you deleted a pair, right? E1 and EM, that's itself a pair. So when you add that back, you get a partition of all of the edges into pairs. Right, so adding back E1 and EM yields a partition of all edges incident to x naught into pairs. Okay. Now, this might be, so this might be really uncomfortable for a lot of you. So the first time I took this class and I saw a proof like this, I was kind of like, what is this? Right? Like, it's very different from the type of math we've maybe been doing. There are very few equations. It's basically just a couple of paragraphs. It's just talking. Now, the features that make it a rigorous proof are it's very precise, that all the words that are being used are precisely defined. Remember, the two features a proof should have are that it should be clear and correct. There is nothing in this text that can be interpreted in multiple ways. So even though I've said some things that are kind of like, seem kind of hand-wavy, like repeating the same argument, it's actually very clear what I mean. So this is kind of the main point of having graph theory in this course. We're going to see a lot more proofs that are kind of like this. And again, the same principles of proof writing we used earlier are important. The logical structure is important. The use of naming things is important. It was important that we named the walk C. We named the vertices in the walk so we could carefully reason about them. Any questions about this proof? Okay. Let's take let's prove one more neat thing, quite easy to prove about graphs, called the handshaking lemma. So handshaking lemma is a statement that for any graph G, the sum of the degrees of all the vertices in the graph is equal to twice the number of edges in the graph. So in particular, the sum of the degrees is even. Let's prove this. Okay. So the idea of the proof is not very complicated. So let's again have a running example of a graph. So in this graph, there are 3 edges. And what are the degrees of the vertices? Well, they're 1, 3, 1, and 1. And indeed, if you add all these up, you get 6, which is 2 times the number of edges. What this is saying is that this is not a coincidence. Now, the way we're going to prove this is we're going to count the same thing 2 different ways, which is something you learned in the counting section. And the thing we're going to count is incidences between vertices and edges. Okay, so let S, or let's call it A, let this be the set of all pairs E comma V such that E is incident with V. So in this example up here, what are the incidences? Well, there are 3 edges, and for each edge, there are 2 incidences. So for this edge, it's incident to this vertex, and it's incident to this vertex. For this edge, it's incident to this vertex and this vertex. And similarly for here, this is incident to, each edge is incident to 2 endpoints, right? So now we're going to count these incidences in 2 different ways. So count A, or the cardinality of A, in 2 different ways. So method 1. So how do you uniquely define an element of A, an incidence? So to uniquely specify an incidence E comma V, let's do it in 2 steps. First, you choose an edge E in the graph. And there are cardinality of E ways to do this. And then when you've chosen the edge, now you have to choose a vertex incident to that edge. So choose a vertex in the graph incident with the edge E. So given an edge, how many vertices are incident with that edge?
2.
2, yeah. So now this is independent of the number of edges. So by the product rule, the total number of ways is just 2 times the number of edges. And now let's use another method, method number 2. Now I'm going to do it the other way. I'm not going to choose, I'm going to choose a vertex first. So choose a vertex V in V. And now given the vertex, I have to choose an edge incident to that vertex. So I'm going to choose E incident with the vertex V. Now V is fixed here. And this is what the degree is, right? The degree of a vertex is the number of edges incident with the vertex. So the number of ways to make the second choice depends on the first choice, their degree of V ways. And the number of ways depends on the vertex, but that's okay. We just apply the sum rule. So by the sum rule, the total number of ways is the sum of all of these things. And therefore, these 2 things have to be equal, right? These 2 answers have to be equal. And that's it. That's a proof of the handshaking lemma.
Good question.
Yep.
Could you define the degree of a vertex as the number of times it's in the edge set of the same graph, and then do the proof that way?
Yeah, that's the same thing. That would be the same. I've just used the word incident. We just use these words because this comes up so much. But it's actually the same thing. Although what you said is a little bit wrong, because the edge set is a set of pairs of vertices, right? So vertices never appear in the edge set. I think you mean the number of times a vertex appears in an edge in the edge set. But you're right. You're absolutely right.
Yeah, that's what I meant.
Yeah.
Thank
Yeah.
you.
Oh, I see. Someone is saying unless you have a multi-graph. No, that's okay. Even in a multi-graph, you can define incidences this way. It would actually work out. Okay, so so that's all I wanted to say in the beginning. Any questions or comments about this? So here's one interesting consequence of this. Yeah, so Ian is asking, oh, do you add to the degree if you have a repeated edge? The answer is yes, because look at the way we define degree. It's the number of incident edges, right? Not the number of neighboring vertices. So indeed, if I had a multi-edge, if I repeated one of the edges in this picture, the degree would become 5. That's correct. So this works for multi-graphs. Okay, so what's a consequence of this? A consequence is in any graph, okay, so Ian is asking, does it count as the same as if the vertices are switched around? So the vertex, that doesn't, sorry, what does switched around mean? Yeah, they're unordered, exactly. So the edges are unordered pairs of vertices. So switched around doesn't actually mean anything in this context. Okay, so one interesting consequence of this is in any graph, the number of vertices with odd degree is even. Does anybody see why that's true?
Would it be because the total degree is even, and thus if we have something with odd degree, there must be another thing with odd degree such that they add to make an even degree in total?
Yeah, that's basically the right idea. So you can work this out using modular arithmetic mod 2 if you want, but this is one nice consequence of this fact. Okay, so yep.
In any graph, the number of vertices, what degree is even?
Odd degree.
So, okay.
So it's certainly true in this graph. In this graph, all the vertices have odd degree when there are 4 vertices, but this is just always true because of the handshaking lemma. Okay, let's look at some examples before moving on to. So let's look at some examples of graphs. They're really families of graphs. So one graph that I like is called the cycle graph. Cycle graph consists of n vertices arranged in a cycle. Okay, so formally the vertex set is 1 through n, and the edge set is the set of pairs x comma y such that x minus y is congruent to 1 modulo n. So you need this modulo n because you have to wrap around to the cycle graph on n vertices. Another graph which comes up a lot is a complete graph on n vertices. So this is just that you take a bunch of vertices and you just put in all the possible edges. So this is this is called K sub n, complete graph on n vertices. So this is K4. And the vertex set here is again just a set with n elements, and the edge set is all subsets. Okay, and then there's something called the complete bipartite graph. on m times n vertices, or let's just say on n squared vertices, or n times n vertices. And here, the vertex set is a Cartesian product of this set with itself. And the edge set is a set of all pairs. Oh, sorry. This is not the same. These have, what am I saying? I need to give this a different, it's not a Cartesian product. It's, it's a Cartesian product of this with the set 0, 1. And the edge set is the set of all, actually, I'm going to save this for later. I'll do this later. Okay. Okay, actually, that's, I'll come back to the examples a little later. Let me get to the theorem I wanted to prove. So here's a definition. A graph G is two-colorable if there is a function f from the set of vertices to two colors. Let's just call them red and blue, or red and green, since I'm using a blue pen. Such that every edge, let's say x, y in the graph, satisfies that the endpoints have different colors. So let's look at our examples and see if this property is satisfied. So let's look at, I don't know, let's look at this graph, just a single edge. Is this graph two colorable?
Yeah.
Yeah, you just color this red, and then you just color this green. So that's okay. What about this?
No.
No, why not?
If you choose one vertex to be red, then at least one of the adjacents have to be green, which leaves no options for the last.
Great.
vertex.
So if you make one of the vertices red, which you have to do, then you have no choice but to make both of these green. And then this is bad, right? So this is not two colorable. What about this?
Yes.
Yeah. And what's the coloring?
Just red, green on the top, and green, red on the bottom.
Yeah, so you have red, green, red, green. So we solved these examples pretty easily, but here's a sort of remark. It's not, if I give you a giant graph, it's not super obvious how to solve this problem, because how many colorings are there of a graph? So a graph with n vertices has how many colorings?
Is it 2 to the n?
Yeah, it has 2 to the n colorings. So, if you have a big graph, it may not be clear how to find one, right? So there's a lot of colorings. So now what we're going to do is we're going to prove a nice theorem saying it's actually very easy to figure out when a graph is too colorable. And it's even easy to find the coloring. So I'm going to state this as, so here's the theorem. A connected graph G is too colorable if and only if. So if means if and only if. Have I used this before in the course? I've already forgotten. Have I been using this?
Yeah.
Okay, good. If and only if it does not contain a circuit of odd length. Okay, so this connects a bunch of the concepts we've talked about in this lecture, right? We assume the graph is connected. And then what this is relating two different concepts. One is two colorability, which is this thing that you need to find a coloring of the vertices so that every edge has endpoints of different colors. And the other is something that looks completely different. It's asking it does not contain a circuit. So remember, a circuit is a path where the beginning and the end are the same. And odd length means odd number of edges, just to remind you. The length of a circuit is the number of edges, right? So here, or here. The length of a path is the number of edges, and a circuit is just a path which has the same end point and beginning point. So it's a cool theorem because it connects two different concepts. So let's prove this. So in a way, what this is saying is that these two examples we looked at earlier, these are kind of the whole story, right? So this has the middle example, this has a circuit of length 3, right? So, okay, and it's not too colorable. This does not have any circuit of odd length. And so the theorem is saying somehow this being colorable or not is really determined by the lengths of the circuits. So let's prove this. Any questions for the statement before we prove it? Okay, so let's prove the forward direction first. So that is, if the graph is too colorable, then it does not contain a circuit of odd length. So we're going to prove the contrapositive. Okay, so we will show the contrapositive. So what does that mean? Assume it does have a circuit of odd length. So assume G has a circuit C. And again, it's it's good to give everything names. So what names do we want to give this? Yeah, let's assume it has a circuit C. Yeah. Given by x0, x1, x1, x2, all the way up to xn minus 1, xn, where n is odd, right? That's important. So now we need to show it's not too colorable. And we're going to do that by contradiction. Okay, so assume F is a coloring. So, okay. So yeah, the V, I guess G is, I'm always using the G is equal to V comma E. So now I've put a bunch of stuff on the table, right? So I've put a circuit on the table. And importantly, the number of edges in the circuit. So 1, 2, 3, 4, 5, 6, 7 is odd. So this is an odd circuit. C. And it starts at some vertex x naught. And this xn is equal to x1, right? So let's assume it has an odd circuit where n is odd. So because it's a circuit, I know that this xn is equal to x naught. So the idea of the proof is pretty simple. So key observation I'm going to make is, let's assume so there's a coloring, right? So the first vertex has some color. Let's just say it's red. So we break into two cases. So case one is that the color of the first vertex is red. So the idea of the proof is pretty nice. What's going to happen is, well, this thing is a two coloring. So on every edge, the color has to change sign. So x1 has to be green. And then x2 has to be red. And then x3 has to be green because it's a coloring. x4 has to be red. x5 has to be green. x6 has to be red. But this is now a problem, right? Because I have two neighboring vertices that are both red. And what I'm going to show is that this always has to happen because the length of the cycle is odd. Okay, so what's the key observation? Observe that the endpoints of each edge are different colors. I mean, that's just because it's a two coloring, right? So, well, so the color of x1 is green, color of x2 is red, and in general, the color of xi. Now, what's the pattern here? Can somebody see the pattern?
The even numbered vertices are red and the
Yeah,
odd.
this is red if I is even, and green if I is odd. So this is a key observation, that the colors have to alternate just because of the definition of two coloring. But now, n is odd. I have to use that somewhere, right? So n is odd. So what's n minus 1? N minus 1 is even. So thus f of x n minus 1 is red, since n minus 1 is even. But now what's the problem? Why is this not allowed?
Since it's like odd number of points, so there must be one that cannot be paired and like repeat.
No, that's not it. You're forgetting about the order. So the order in the circuit matters, right? Like, let's look at this picture here, right? let's give these edges names here. Let's call this E1, let's call this E2, and let's call this last edge En, right? I claim that one of these edges is violating the rules, violating the property of being a two coloring. Which one is it?
The last one.
The last one, yeah. Because remember, I started off with saying that, hey, f of x naught is red. And I just conclude, now f of x naught, that's the same as f of xn, because x naught is equal to xn. And now I just saw that f of xn minus 1 is red, right? So now I have thus f of xn equals f of x naught equals red equals f of xn minus 1. So the last edge violates the coloring. So f is not a valid coloring. So f is not a two coloring, which is a contradiction. So that's it. That's the end of the proof of this direction. Well, okay, there's a case 2, which is f of x naught equals green. And this is completely analogous. In fact, it's so much the same thing. I could have assumed without loss of generality that f of x naught is red. Otherwise, I could have just switched the roles of green and red. But let's write it this way. Okay, so that's the proof of one direction of this. Any questions or comments? The logical structure is kind of complicated, right? So I proved the contrapositive, but I proved the contrapositive by contradiction. And the reason that was helpful is assuming something has an odd cycle is more useful than, I mean, maybe more useful than assuming it has. I mean, okay, I could have done it a different way. I could have assumed it's two colorable, and then I would have had to assume for contradiction it does have an odd cycle and then do the same thing. But anyway, this worked out. Any questions or comments on this? Okay, so now that's only half of it. We have to prove the other half. The other half is if it doesn't contain an odd circuit, it is two colorable. So let's do that. This part is actually slicker. So we didn't use that it's connected for the first direction. And the second direction, we're going to use that it's connected. The second direction is actually quite slick. The second direction, I'm going to assume G is connected. And now I'm going to do something that seems a bit weird. I'm going to pick an arbitrary vertex. So let x in V be an arbitrary vertex. So there's some cartoon of a graph here, and there's a special vertex x in here. And I assume that the graph has no odd cycle, right? So assume G is connected, assume G has no odd cycle. I guess I could have put that earlier. And our goal is to construct the coloring. So we will construct a coloring, a two coloring of the graph, just using that it has no odd circuit. I mean, I guess I should have moved this arbitrary vertex. It's better writing to move this arbitrary vertex later. So I don't know how easy or hard that's going to be, but let's move this here. It's actually kind of worked out. So you choose an arbitrary vertex, and now we're going to do a kind of very clever thing. Now we need to, so we're going to color this red. So let f of x be red. So we'll construct a two coloring of g, which is a function from the vertices to red and green. So I'm going to just color this one red. And now what I'm going to, now I have to define the coloring everywhere on every other vertex y. So this is pretty abstract because I'm doing this in a general connected graph, right? So the key idea is, it's kind of inspired by what we did in these cycle examples. In this example here, how do we construct the coloring? Well, we had this even odd thing, right? So one way to think of that is you fix a starting vertex. I mean, there's a different way to think of that. You fix a starting vertex and you color everybody at distance 1 the opposite color. And you color everybody at distance 2 the opposite color of that, and so on. And this is now, it turns out, going to work in a general graph if there's no odd circuit. So let's see how that works. So now I'm going to define a function. So for every vertex y and v, I'm going to define the distance from x to y to be the length of the shortest path from x to y. May not be unique, but length of a shortest path from x to y in G. So this dist function, this is a function from pairs of vertices to positive integers. Or I guess for every, okay. Yeah, I guess we'll define the distance to be 0 if you put x, but that doesn't matter here. So for every y, there is some path from x to y, at least one. Why is there a path from x to y?
Because it's connected.
Because it's connected, yeah. So there is some path, and there has to be a shortest one. Because the length of a path can't be less than 1. So there's a shortest one. I'm going to define this function. So now I'm going to define the coloring. F of y to be red if the distance between x and y is even, and green otherwise. This is now a valid function defined on the vertices of the graph. It's based on the distance to this initial vertex x that I picked. I picked it arbitrarily. It didn't matter which x I picked. So it's a pretty sophisticated proof because this x is playing a very important role. It's allowing me to define this distance function. But any x will do. I just need to pick one. Any questions so far on what's going on in the proof? I mean, right now, it might just seem like a stupid idea. We haven't seen why it's a valid 2 coloring. Okay, so now the key claim is this is a valid 2 coloring. That is, for every edge in the graph, the 2 endpoints have different colors. So let's prove this. We'll prove by contradiction. So assume for contradiction that it's not. So assume f of A equals f of B for some edge AB in the graph. Okay, so I'm going to draw a cartoon here. Here's A. It's connected to B. And I'm going to assume they get somehow the same color. I'm going to show this is impossible. Any ideas what I should do? So given what I've already told you of the proof, what should I look at? I went through all this trouble to construct this distance function. Any ideas on what I should look at?
Should we consider their distances to the point that we had x? Or
Yeah, let's do that. That's how the function was defined, right? So x is some vertex sitting out here, and there's some shortest paths between xa and xb. Let's give them names, right? So let PA be the shortest path from X to A. So this is PA. And now for reasons that'll, so this path goes like this. And now I actually would like to, so let PB be the shortest path from B to X. So this is going in the other direction. So I just take the shortest path from X to B and reverse it. And then I get a path from B to X. Okay. Now these two things have the same color. So what can I say about the lengths of these paths?
The length of the path is not odd, so it's even length.
Well, let's look at the definition of the function. The function is saying all the reds have even distances and all the greens have odd distances. So if these two things have the same coloring, they must both be even or both odd, right? So this is the key observation. So this is PA, this is PB. But the way I'm going to phrase it is actually like this. So now consider the path PA followed by the edge AB followed by the path PB. So I'm going to complete the loop like this. Let's call this path C. Well, this is actually a circuit, right? Because it starts at X and goes back to X. And the length of this is the distance from X to A plus the distance from X to B plus 1, because I have this one extra edge that I put in the middle. But now the beauty is that the sum of these distances, the first two distances, has to be even because they're the same color. So they're both even or both odd. So notice that the sum of these distances, this is even since both terms are even or both are odd. And the reason is because f of A equals f of B. Well, if this is even, then C is an odd circuit. So thus, C is an odd circuit. And that's the contradiction we wanted to prove, right? That's a contradiction because we assumed C has no odd circuit. So this is a contradiction. That's the whole proof. That there can't be this, you can't be in this bad situation where both of these things are the same color because the sum of their distances is always even, because they're either both even or both odd, and you'd create an odd cycle. You create an odd circuit, sorry, if they had the same color. Okay, so this was a lot. This is way more sophisticated than the proofs we've done earlier in the course. So it's okay if you don't understand it while I'm doing it, but you should go back and read it carefully. I want to end with one remark, which always confuses people with this proof. So why did we use shortest paths here? Why couldn't we use some other path?
Because that's how the distance function is defined.
Yeah, it allowed us to define a distance function. Yeah, that's one way to view it. Well, we could have chosen some other longer paths, but then then we would have had trouble defining f, because we would have had to prove that the lengths of all those paths are the same. That's actually true if you don't have odd cycles, but it would have been annoying. So we could have done this with paths other than shortest paths, but so we could have used any path from x to y to define f of y, but then we would have had to prove that they all have the same parity. They're all either they're either all even or all odd. So just to avoid this annoyance, we use the shortest path. That's why we use shortest path. Anyway, that's the proof, and that's the theorem that two coloring is equivalent to not having an odd length circuit. So anyway, that's it for today, and yeah, see you next time.
One quick question.